Okay, so I have maybe one or two more at the most, but I'm not going to stay real long because I got to go eat dinner too before 10 o'clock. And Ben looks like he's almost ready to fall asleep.
No.
No?
I'm okay.
I bet I was awake. Normally I can't say this. Normally I bet I'm just about the last one awake. If we look at everybody's wake up time, I'm probably the last because I usually get up like at 9. Does anybody get up after 9? You do? Okay. All right. Sometimes. Okay. Well, anyway, but today I think I probably got up before any of you. So that's okay. I just have to win once. One day I can say I was an early worm, early bird getting the worm, whatever the phrase
You're
is.
an early worm.
I'm the early bird getting the worm. Sorry, I forgot the saying. Okay, so prove that f from x tau to y tau prime is continuous if and only if for all capital F closed in Y, the preimage of capital F is closed in X. So the main proposition that we learned, by the way, that thing I said that I would ask you at graduation, stop the music, we're going to have a quick final quiz before. Probably a good idea to make sure you know that pretty well, because I've been really excited about that, and it's really important. So that proposition says that preimages of open sets are open. So this is asking you to prove that, well, it's just as good to say that a function is continuous if preimages of closed sets are closed. Okay? So it's very related to the other proposition. So maybe we can even use that. Okay. Did anybody try this problem yet? It's one of the ones on the practice.
I looked at it.
Did you look at it? Yeah. Well, good. We should just do it now. That'll save you the time of worrying about it later. So, you've got two directions to prove. And actually, we might even figure out that some of it's just reversible. So we can just do part of it. Let's see. So let's assume that f from x tau to y tau prime, excuse me, is continuous. Okay. I would like to show that preimages of closed sets are closed. So, yeah.
Or I don't know if I'm speaking too soon, but since we know that, can we use prop 10 and say like u we can use a u that's open, and then
It's technically prop 8.
or prop 8.
But that's okay. Again, the numbers don't matter. I just want to make sure everybody's clear.
If I can use that, can I relate that to, okay, well, u is open, I can say that x, or in this case, y minus u is equal to f, which is closed. Could I somehow make
Okay, so that right there is where you got to be careful. Because you started with an open set u, and then complemented it into a closed set, which you then called f. And I would say, you have the right idea, but I would say you should be starting with f. Because the proposition that you're proving starts with f. Don't start with u, start with f. And then, of course, you can take the complement of that and call it u. You have exactly the right idea, just in the reverse order of how you want to present things. So we're going to, if it only, yeah. So suppose that, say it again, Sarah.
Suppose f is closed in y.
Right. Suppose f is closed in y. You have to start with that, right? And then, what do you want me to do, Jose, there?
Oh, then f is equal to, or like the complements are f is equal to x minus u, which is open.
Right. Okay. So then f is equal to x minus u, which is where u is open in y, right? Okay. the pre-image
but,
holds.
but I'm sorry, by prop A, the pre-image of U would be open in X.
That is true. Okay, I'm gonna put that over here on my scratch paper. Okay, that's gonna be good. But what am I really trying to show?
The pre-image of X.
This, right? So let's grab this and see where we can go with it, right? So, pardon?
So I have a question. So you have f is a subset y and f equal us minus u. This has to be f
Oh,
equal y.
I'm sorry, this is supposed to be y, that's a typo. That's a mistake. That f should be y minus u.
Yes.
Did everybody catch that? Sorry, it's on the output side. Thank you. Yeah. Okay, so this is what I want to work on, right? So now this is, you know, the pre-image of y minus u. Okay? This would be the elements of x that don't get mapped into u. Right? They get mapped outside of u somehow. I mean, we can draw a picture if it will help you. Here's x, here's y, u is right here, right? So obviously the pre-image of u, we don't care about that. We're looking at the pre-image of y minus u. We care about this part right here. This is y minus u right there, right? This piece of it up here. Okay, so we want to use this information. Somebody made this. You would get partial credit, of course, for writing this down, that this was a proposition that was helpful. So showing all of your work is good. If you have all the pieces, but you didn't assemble them correctly, or you didn't really know how to put, you knew it was proposition A, you knew you needed to use this on. If you please write it all down, even if you don't have it pieced together perfectly, because I'll give you points for knowing the knowledge of it. I may not give you full points if you haven't put it all together quite right, but yeah, we definitely want to use that. So can we relate, is there somewhere to bring this into the picture? Because I don't see pre-image of u here. Do we know, is there a way that we can write this now that might be helpful to us? Like, what part of x is this here? So right here, this is the pre-image of u.
This is a complement.
Yeah, I claim that, guys, that this is just x minus the pre-image of u. This is a key step right here. Right? Probably if this was on a homework assignment, I would want you to prove this. I'd pick something here, show that it lives here. Pick something here, show that it lives here. You could ask me, this would be one like during the test, you might say, I wonder if I need to prove that, or whether it's kind of clear from the picture or whatever. You could ask me and I would tell you. In this case, probably for the in-class test, I would say, no, you don't need to actually prove that. Again, this goes back at least to 8, math to 8. This is not like a 414 exciting thing, so probably I'm not going to want you to waste valuable minutes on this. Okay, but the point now is that you have, this is an open set, and we're taking the complement of it, right? So then this is closed. Which is closed. I'll just say since the pre-image of u is open in X. Great. So that would pretty much do it. How would you do the reverse proof? You're assuming this, right? You're assuming that pre-images of closed sets are closed, and you're being asked to prove that the function is continuous. How are you going to prove that the function is continuous? Are you going to use the definition? Are you going to use... Which of those propositions do you think you'd want to use? I would want to use prop 8. I would prove that f is continuous by relying on Prop 8, which says that preimages of open sets are open. So that's exactly right. So I'm not going to maybe write out this whole proof, but to prove F is continuous, right, I would let, U be open in Y, right? And then I have to show, we need to show that the preimage of U is open in X, right? And I would, of course, right away turn this open set into a closed one, right? And that would just be the complement, right? So we know that Y minus U is closed in X. It's basically, it's more or less reversing what we did before, right? This is like the capital F now, right? So by assumption, the preimage of this is still closed.
Be closed in Y.
It'd be closed in, oh, did I mess this up again? We know that, oh, I sure did. Sorry, this is closed in Y again. I made the same mistake. Right, so Y minus U is closed in Y. So I'm going to take the preimage of it, and by assumption, that will be closed in X. And then I'm just going to use this again, actually, right, to finish the proof. So it basically, I'm going to let you guys, I have the solutions because I got the practice quizzes, and this is one of the problems from the practice quiz. I might let you guys try that one. I want to do one last example, if you'll let me. I just have to find it here quickly. Okay, yes, I found it. Okay. One last problem. This will be it, and then I think sleep will be. After I climb a mountain, I always need three things. I need a shower, I need food, and I need sleep. And it's usually in that order, I think. So I didn't climb any mountains today, but I feel like I need all three of those things. So I'll probably, after we're done with one more example, I'll probably do that. Okay, so this is number 7, last example. So let's see. So X is equal to R. I just found this problem today in another book, and I thought, oh, this is a nice problem. Let tau equal the set of, okay, look right here, guys. It's a set of sets. Okay, that's what topologies are, right? It's a set of sets such that, okay, so this is, you have not seen this one before. It's a little different. For each X element of U, there exists an epsilon greater than 0 such that the interval from X to X plus epsilon, and it's closed on the left side and open on the right side, is contained in U. So the idea here is that, so here's the real numbers. If you take, so U is somewhere inside of here. It doesn't have to be an interval necessarily, but if you take any X that is in U, like normally you're trying to put a whole neighborhood around X, kind of to keep it inside some open interval. This is a little different. This is just saying you've got to be able, this is not really quite the same as the definition of an open set. It's sort of like a one-sided neighborhood. Because you're saying that the neighborhood starts at X and only goes to the right. This is called the lower limit topology on the real numbers. Have you seen this before? Okay. You look like you were, you're just excited about it. Yeah. So it turns out this is actually a topology. It actually works. But I wasn't actually going to, I wasn't going to prove that it's a topology for now. So let's assume it's a topology. So this is a topology. Take that for granted. It's pretty clear that it's got the empty set, the whole space, the whole real numbers in it. You have to show that it's got the finite intersections and arbitrary unions. Okay, let's just let that go. Okay, we'll just assume it's a topology. So then what I'm going to do is I'm going to define f from x tau to itself via f of x equals x squared. So this is just the real numbers to the real numbers. It's our usual x squared function, but we're using a different topology, and I claim that with this topology, f is not continuous. So I would like to show that f is not continuous. So you're disproving something, and you know, it's a great opportunity to show maybe some kind of a counter example. Right. So the open sets are kind of going to be subsets of R that have this condition, that any point within the set. So for example, anything of this form is open. Okay. Anything of this form is open because if I, again, how do I define open in this context? So, I mean, if I literally pick, let's just pick a particular interval here. Actually, let's just pick, okay, I'll just pick 2 to 3, something like that. Let's call that U. Is that in tau? Well, let's see. Is it true that for every x in U, so this x, for every single point in that interval, is it true that I can build a half-open interval of this form that stays inside of U? Absolutely, right? I mean, if I pick this one right here, well, I can make that kind of a half-open interval. Even if I'm way over here, I can do it. I just have to make it very narrow, right? Okay, so those, for example, would be open sets. Hi, everybody. Hopefully you were listening, and now you can see the picture of what you just missed. The nice thing about the video, you can pause it now and figure out what was the guy talking about. So anyway, that's what we're talking about here. So basically, we're creating a new topology that I've never had a chance to show you guys before, just to practice on. And we are going to try to show something weird happens, which is that a function we normally think of as continuous is not continuous in this topology. So how do you want to show it? Mackenzie, do you have an idea?
If we're picking, okay, well, I'm thinking that because x squared is symmetric, then it's gonna only go, it's gonna go to both sides, but we need it to go to just to the right.
So it shows the interval from 0 to positive infinity.
Yes.
I'm gonna choose a,
You're going to choose an open interval? Or you're going to choose this interval?
yes,
Okay.
this one.
I would agree. Okay,
And
this
the pre-image of that.
this is
already
open. Okay, what is the preimage of that? Under this function, which inputs into this function will give you an output that's in that range?
Is it from negative infinity to positive?
You have an open set, the preimage still open. The whole space is always open, right? Okay, so what does that prove? Anything? This is showing me that, This is showing me that there's a preimage of an open set that's open. That actually doesn't prove anything for us. because we need, so I like what Sarah's doing, she's trying to show that we can start with an open set whose pre-image is not open, but this is not the best open set to work with, as it turns out. And sometimes you have to try a couple times. Actually, I have to do this too. Like, I don't always come up with the right thing to use. See?
Any negative x, -1 plus epsilon would work. That's open and
So, give me your set U, I'm sorry.
-1, comma -1 plus epsilon.
I need to know, if you're creating a set, I have to know what the set is. So I don't know what epsilon is right now. You want to make it up? You want to, make this, plus 0.01 or something? I don't know.
Yeah.
Well, that would be, okay, so you want to make this interval right here. Okay, that's fine. That's an open set in our topology. And what is your claim?
Well, like when you take the f inverse of that open set.
The pre-image.
Sorry,
I know, it's awful. The notation is awful, and it probably really bugged you on the take-home test. But anyway, what is the pre-image of that set? Which inputs to the function will have outputs in this range? None, which is also open. So, 2 strikes. I need somebody to come save us here. Jose?
Is there somehow that we can use proposition 10 and, because like, I know there was a remark that proposition 10 is best to show that functions are continuous.
Well, when I say it's best, I mean it's a good tool for disproving continuity, and it's not so good for proving continuity. So if you're asked to show that a function is continuous, I would not use proposition 10 because it involves arbitrary sequences that you would have to consider. If you're disproving continuity, as we are here, then I feel like using sequences is definitely a good idea, but you don't necessarily have to do that. Yeah.
Can we make a set that includes partial negatives and partial positives then?
Okay, give me an example.
So we could just use -1 to 3.
Okay, let's take that. Okay, what's the pre-image of that? So this is open, I agree. Okay. So which inputs are going to fall into that window?
From 0 to the, or no, it would be, only the things that would be positive in this one would come from,
I mean, maybe it just helps to draw the parabola. So here's x squared, and 3 is somewhere here. So we're looking for which inputs stay below 3 and above -1. Here's -1, here's 3. Well, this is going to be the square root of 3, I think. Yeah, square root of 3 does it. And then this is so this is just going to be negative the square root of 3, right? So we actually have, but not including those numbers, right? So is this one just going to be this interval like that? Right? I think I have it right. Is that open?
Yeah.
Unfortunately, it is. And we only have like 10 people in this class, so we've only got about 7 more people to try to come up with it. Yeah, this one is also still open because if you pick any point in this interval, you'll be able, if I draw negative radical 3 to radical 3, if I pick any x in there, yep, I can make one of those weird intervals like this that stays inside of there.
It's just 0.
You want to use just 0.
Oh, it's never close. Just kidding.
That's okay. Yeah, we have to start with an open set.
Yeah.
Okay. You're all around it. Like you guys have given me like 3 ideas that have almost been right. It just hasn't quite worked. Let me bail you out because I want to get out of here too. So if you just use, you are the closest, but the thing is you don't want to use the negatives. So if you just actually use the set that I put over here in the first place, it works wonderfully because the pre-image of this, I claim, is not open. The pre-image of this is going to be, so here's 2, and here's radical 2, right? And here's negative radical 2. This is going to be the interval from negative radical 3 to negative radical 2 like that, union with radical 2, radical 3. Okay? And this might be too hard for the test, but it's still a nice little problem to think of. So which inputs land in here? Well, they're x's that are plus or minus of radical 2 to radical 3. Right? But not including the radical 3 part, including the radical 2 part. This right here, my friends, is not open. Why not?
It's not of that form.
I mean, so here you go.
It must include the,
What's it say? For this to be open for each x in U. Here's an x that's in this set, right? Because I'm including that point. And I don't care how small your epsilon is, when you make that little sort of half open interval thing, it is not possible. This is bad news right here. It is outside of the set U, you see. Right? So this is a pre-image that is not open in the domain. Jose, I actually really like your idea. You might think a little more about how you could use sequences here, you know, to make this work. Find a sequence. I didn't talk much about convergence of sequences tonight. You should review that. I mean, even though I didn't do it tonight, it's still something you should know about. But I think I've given you an idea, right? Kind of a few more practice problems. I hope that's pretty helpful. It's already about 9:25. I was kind of hoping to call it a night. Is that okay? Or do we have more questions for me?
I have a very specific question.
A very specific, about the review or your own?
It's from the practice.
Okay, before I take that question, does anybody else have any questions? Maybe I actually just turn this thing off. Okay. And the answers to the exam are, oh shoot.